Steve Sims has been doing a great job chairing this version of LUG this year. I think we should give him all a round of applause for his efforts. Steve's going to be giving a talk now about DNE2 testing at Lustre 2.7. Steve is at Indiana University. He's a board member representing the community. He does a lot more than you would see him do. He's a fan of Marvel and movies and music, very cultured, and has a fantastic beard and a wonderful voice. Please welcome Steve Sims.
Thank you, Beardman.
You're welcome.
I'll let you do the computer thing.
Well, thanks. Thanks for that lovely introduction. About to cry. You've heard a lot from me today, and yesterday, and the day before. My name's on here primarily because Nathan Lavender really hates public speaking. Are you out there, Nathan? Where are you? Right on, man. I mean, for some people, it's really a question of death and public speaking. I was there once, so I really can relate. So he and Tom Crow work for me, and they did really the bulk of the heavy lifting here. So I'll do my best to present, and if there are any difficult questions, perhaps you can talk to Nathan later. So our abstract more or less was about how everybody at IU needs more metadata performance. And, you know, we through the grace of vendors, we were able to get some loaner equipment and some free equipment. And so we did some testing. Now, I'm going to begin this by saying, again, scaling for Chris Moran and scaling for Steve Sims are two very, very different things. So, with that, I'm going to move forward. So, DNE Phase 1 permits you to have multiple NVTs on one or more MDS nodes, and you can assign your MDTs to a particular portion of your directory tree. So, you know, if you have Bob Davis in the We Write a Lot of Zero-K Files department, you can assign them to their own MDT, and they can make themselves suffer. So DNE2, I mean, from an administration standpoint, it's kind of cool, because you get the benefit of striping without having, directory striping without having to do that sort of assignment. So here's a picture. As you can see, there's kind of a parent MDT and sort of child MDT, or, you know, remote MDT. As you can see, files and subdirectories in both cases end up on that particular MDT. So for DNE2, you can see that we have striped directory 0 across 3 MDTs. Files that are written in that directory will be striped across the MDTs. And as we can see, subdir 1 is also striped. And subsequent files written into that directory would also be striped across, or, you know, I mean, to be more precise, their metadata would be then striped across MDTs. So here's a story at IU. We support 150 plus disciplines, ranging from people doing lighting simulations, people doing textual analysis, computational chemistry, high energy physics. So we run the wide world of sports. Tons of different I/O patterns. Right now we have a single MDS MDT configuration, 24 SAS drives. We're approaching 1 billion inodes, and we're at 216 with intentions to move to 2.5. but we are very interested and curious about DNE2 and wondering if we could combine SSD with DNE2 and what might happen. So these are the boring statistics on the servers we used. We designed each one to be identical so that we could use them in different combinations of MDSs or OSSs, and we knew really kind of what we were getting. For those of us that can't read, here are the pretty pictures. The important I/O stuff is we took a smart array controller, plugged it into, let's see, from this angle, the left portion of the DL380, and then that was then populated, each was populated with 6 Intel SSD drives. In the metadata, I mean the maximal metadata configuration, on the right side we had 20 Dell power edges. On the left-hand side we had each of these building blocks connected together into an FDR network. So the logical setup, I mean, the take-home message from this slide is that we assigned a single MDT to each one of the drives. You know, so we had a SAS drive, 6 SSDs, and we had a one-to-one correspondence between MDTs in each drive. Because it takes a long time to format stuff, we had 50 gig LUNs, so we could reformat and hurry. We had 8 gigabyte journal. Lazy itable init, that meant that after the format, or more, sorry, we wanted to make sure that the format was done before we proceeded, because we didn't want any additional I/O. So we used MDS rate. That's the Lustreware metadata benchmark. It's in the Lustre test suite. We wanted to avoid, at least for these tests, having to use OSSs and OSTs because there are too many variables there. So we wanted to try to limit the variables. We used make node. I mean, we did make node stat and unlink, and the stat and unlink slides will be in the appendix, but we'll just talk about the make node data today. So we did a wide parameter sweep. We had these 20 Dell clients with 32 mounts each. So we had a total of 640 mounts, and that was to simulate 640 clients. So we varied the number of directories from 1 to 128, and we wrote 4 threads per directory. And we found that that was kind of a sweet spot. And again, we didn't want parameter central. We wanted to try to narrow things down. And so we increased the stripe count across the directories as we increased the matching MDT count. So we tested 3 different configurations: 1 MDS, multiple MDTs, multiple MDSs, a single MDT per MDS, and then multiple MDSs with multiple MDTs per MDS. So as you can see, I mean, adding MDTs to a single MDS got us some increase in performance. This sort of shark fin thing that you see, we graphed it so that the highest went to the lowest, more or less to show you that the first run, each low point was the first run. Now, you know, maybe this is cache warming. Maybe you guys can tell me what that is during Q&A. But we didn't know. I mean, we thought maybe this is some sort of cache warming behavior. Here we have CPU busy. So we maxed out at about 80, which, you know, I mean, the question in my head is, you know, could we have gone beyond 80% CPU? And then we look at the sort of drive busy stats, you know, from IOStat. And, you know, these are averages, so you don't really see the bursty behavior. You know, at the baseline, you add MDTs and performance increases, but, you know, beyond 4, you get diminishing returns. And, you know, frankly, adding MDT, you know, performance is not stellar, but it does help some. So, you know, first trial shows this decreased performance. It correlates with the spike in drive I/O busy. So, as I said, maybe this is some sort of warm-up behavior. In testing multiple MDSs with a single MDT, the scaling is much, much cooler, as you might expect. So, again, performance increases using increased MDSs. Well, we kind of figured. It scales with the same client workload. We had 480 physical cores, so it's possible that and again, it's possible that the sort of variability in the 512 numbers could be related to contention, maybe not. But as you can see, you know, threads above 64, the scaling's pretty linear. So, you know, can we get multi-MDT performance higher? As I said, you know, can we get above 80% CPU? And we can see that, you know, the drives aren't crazy busy. So would it be possible to increase efficiency? And these are open questions. Certainly I don't have solutions. I mean, you know, there are engineers out there to, you know, it's like Zappa says, when you write a composition, you have critics to tell you, you know, whether it was good or not. So you engineers can tell me, you know, what you think. So multi-multi. The best performance we saw was with 6 SSDs and 6 MDSs. That was about 860,000 meg nodes per second. And again, we see the scaling pattern. This is kind of a cool graph. Andreas, are you out there? He helped put this graph together because he's a bad dude. So as you can see, with basically this is the variance as you add MDTs to each MDS. So you can see that you know, the maxes increase and you know with the MDT count, but the points, each one, you know, shows you the MDT count. I'm sorry, the MDS count. Does that make sense? So each blob that you see is the cutoff point for adding MDSs. And you know, the scaling here is linear. So again, metadata performance improves as you increase MDSs and MDTs. But you know, can we scale beyond this? I mean, if you look at the line, I mean, if we were to continue adding MDSs, I mean, we could crack a million, maybe even with an additional MDS. So here's the comparison chart. You can see that, so we got 1 by 2, 2 by 1, 1 by 4, 4 by 1, and 2 by 2. So as you can see, 1 by 2, 2 by 1, and 1 by 4 are all bunched together. 2 by 2 gives you additional performance. 4 by 1 is the one you want to see. So what I take from this is that if you have 2 MDSs, each with 1 SSD, you can get the same performance with 1 MDS and 2 SSDs. So if you're planning in advance, it's probably easier to say, well, we're a broke institution. We could have a single MDS with 2 MDTs, you know, 2 SSDs, and you know, get the same performance plus or minus error, than having 2. So for small numbers, you know, you're fine, right? And if you want just a little additional performance and you can afford to drive, fantastic. But if you want to go whole hog, buy more servers. So there's sort of the summary of the comparison. But really, the big question, and you know, I can't sort of underscore this enough. With 150 disciplines, there are a lot of Bob Davises out there. So if you buy an MDS or an MDT for bio, then you got to buy one for high energy physics, and then, you know, the next thing you know, you're buying a lot of MDTs for a lot of different departments because you want to treat them equally, or you can try to charge them, and that's not always easy. So in terms of having a scratch directory, we'd like to be able to stripe one directory for everybody and distribute the load. So more or less we did the same thing, only with the variable that we changed was using one single stripe directory. And here is the scaling per MDS count. And again, it's linear. So what's the take home here? You know, for years we've been able to scale aggregate I/O by increasing OSTs because we have a sense of what that's going to do. We've done all kinds of testing in that arena. DNE2, or having this kind of data, permits us to figure out, plus or minus error in advance, what kind of resources we need to get what kind of metadata performance. But, you know, when you dig into the weeds, sometimes, you know, you find a flower. Actually, well, you know, you can catch me offline and I'll tell you the whole thing. Is that camera on? So one of the things we discovered along the way is that turning quota off gives you a significant performance bump. But you can also see that with quota on, between 2.5 and 2.7, performance is decreased. So this resulted in a JIRA ticket. And, you know, the feedback that I got from Intel is that, you know, part of this is a Linux piece and part of this is a Lustre piece. And, you know, work on this is in the pipeline. In addition, we discovered that in our scripts that we were running, you know, you could list the devices and you'd see that you had 24 directories available, or sorry, 24 MDTs available. And so in the script, we would then set the dir stripe at 24. But as you can see, after doing a get dir stripe, we really only had 5. So we were expecting 24, we got 5. And it's simply because there hadn't been enough time for the MDTs to kind of come online. So while we recognize that this is a delay and you kind of might need a delay for this to happen, in my world, when you hit return and the prompt comes back and there's no error, then you'd like to believe that the action that you requested is complete. So that's resulted in a JIRA ticket as well. So, yeah, once again, Dell, thank you. You've done your part for the community, and we're all grateful. There's lots more data to be taken. I mean, in any particular situation, there's more data to be taken. It would be interesting to see what's going on with ZFS on MDT. Well, you know, we've seen some data about that before, but it would be interesting to see what those curves look like, at least at the moment. We want to see what happens, of course, when you add OSTs. So we'd like to do some MDS rate testing. And then lastly, we'd like to see, you know, kind of what effect this has on real-world applications. I don't know if you guys know the Trinity code, but there's a portion of that code that writes thousands of files in thousands of directories, which is taking a toll on our system right now. You get a bunch of those guys running at the same time, and it puts the squeeze to your metadata server. So it'd be great if we could help those guys out and other people that have codes like that. Thanks to Matrix Integration for helping loan us some gear. Thanks to Intel for doing the same in the SSD department. The servers we used were HPs. They generously loaned us some gear. Our high-performance file system team, the rest of them, they certainly contributed to what Nathan, Tom, and to a certain extent I were doing. And thanks to our Wrangler partners, TAC and Argonne, because our partnership with them and the serendipitous gift from Dell permitted us to do this work. And so thanks to NSF for that money. And thanks. Thoughts, questions, comments, cliches, and words that begin with C. Giuseppe.
Yes, I have a question about the picture you showed on the comparison between quota. So when you have quota and when you remove them. So it sounds like here you are saying that responsibility for this behavior, you say, might be related to the operating system and to Lustre.
Yes.
But I wonder, why didn't you, I mean, did you try to do this exercise, ceteris paribus, in the sense that you tried 2.5 and 2.7 on the same operating system?
Yes. I mean, Linux. I mean, I'm presuming it was a different
I mean, but the same version, the same Linux version.
No, I don't believe so. Andreas? He's going to fix this up because I'm a moron. James? Oh, I thought you were Andreas. Sorry, I mean, it's the light.
Not even the same hair color, so.
One, you're sitting in the dark, and two, I'm, you know, look, man, you guys can, like, ask me where I was on the 27th. Maybe I'll tell you.
Okay. As an explanation for that patch, basically there was some time ago patches, what we discovered that the quota was not scalable in the Linux kernel. So there was stuff pushed upstream that resolved that. And then, of course, we try to use those backported, those patches to RHEL and that. And it wasn't done correctly. There was stuff missing that was done upstream that wasn't. So now that's been backported and it should work.
And just so I'm clear, you guys pushed something to the Linux kernel and it didn't fix the problem.
No, what went upstream actually did fix the problem. But what happened is because the review process there is a larger scale, and you had quota experts like the guy from SUSE, and they made the patches perfect and they work very well. But the ones that ended up in our RHEL system, they were developed a little bit earlier. They weren't quite correct. So we've now synchronized those with what's upstream, and it works fine now. That's been integrated into master. So what do you mean by that? If we were going to run the same exercise with these fixes, we should have horizontal. I mean, the same performances between 2.5 and 2.7. You should see, well, with this patch, you shouldn't see the hit from the quotas. It should be gone if it's done correctly.
Okay. Okay.
The thing is the patch isn't in Lustre. The fault was in patching the RHEL server side. That's where the problem was.
Patching the RHEL version.
Yeah, the RHEL server side. The kernel has to be patched in order to remove the quota limitations, because it's an older kernel.
Okay. Thank you.
You're welcome.
Thank you.
Thanks, James. Thanks, Giuseppe. Anybody else? Jason Hill, ladies and gentlemen.
You can see this far back, right? James is in front of me.
But James is in the dark there.
Oh,
I mean, you know.
I'm one of the enlightened ones, I guess.
It's your halo.
He's very disarming, you know this, right? So your data sets, is that the best run? The stuff you have on your graphs, is it an average? Is it, you say you have more data points to gather, but...
That 860,000 is the best run that we saw.
Okay. So, were there multiple iterations, or did you just have time for a single? What's the average look like? Or am I drilling too deep for you and I should go talk to...
Well, you know, thanks. I don't have the average number handy, but you can see all 4 trials there. I mean, maybe you have to squint. But, you know, there's the flat line straight across. As I said, I'm connecting the best run to the lowest run, you know, looking for shark fins. But yeah, if we weren't completely under the gun trying to like squeeze this all together, we would have had multiple graphs. Is that a thumbs up? Right on, thanks. Thumbs up from Jason Hill, that's all right.
So, just to, it's Andreas over here.
Sorry, man. James? No. Hey, Bob, was that you asking? No. Oh, Andreas.
So yeah, these graphs, all of the graphs show all of the data runs. There's 4 data runs. And yeah, it's not just the highest connected to the lowest. It was the first connected to the last.
Sorry, but you're absolutely correct.
But the quota thing, there's actually two different patches. There was a problem in Lustre that related, it interacted badly with the version of the patch that was in the kernel. But I think the important thing to note here is that this performance difference is only related to DNE, right? So this dip is because we're testing DNE. If you run with a single MDT, the quota performance doesn't look like this because it was just contention. The kernel quota has a single lock, so even if you added multiple MDTs per MDS, you weren't getting any scaling until after we added this patch. So, you know, there's a patch for Lustre and there's a patch for the kernel, and both of them exist already, and they're landed but after 2.7. So you'd have to patch 2.7 if you want to run, you know, DNE at high performance.
Andreas, are you Canadian?
Yes, I am.
I'm surprised that you were disclosing so much. Thank you for that. Anyone else? Well, thank you all for your time. As I said, there's an appendix.